Hello and welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg, as usual, proudly powered by Research Luxembourg and recording at the Media Centre of the University of Luxembourg. And in today's show, we are coming back a little bit to some of the subject we've already discussed, and you'll see a few links there hanging around because our guest is Dr. Dagny Aurich, who is a postdoc in the Environmental Cheminformatics group at the Luxembourg Centre for Systems Biomedicine, LCSB for short, University of Luxembourg, and she focuses on cheminformatics tools. I have to mention as well that she has background in forensic science and analytical chemistry, so a lot of different directions we'll be going to today. Dagny, thank you so much for coming.
Thanks for having me.
All right. So, of course, the usual way of starting this podcast are definitions. So I already mentioned some of the things, and I wanted to start with your PhD focus. So I wanted to start with exposome and exposomics. There's a lot of omics nowadays. I really still struggle with some of the definitions. So we start with exposome. What is exposome? What were you focusing on in your PhD?
So the exposome concept was first introduced by Christopher Wilde in 2005. And he said that it encompasses all environmental influences and associated biological responses throughout the lifespan, so from conception onwards, basically, including not only exposures from the environment, diet and behavior, but also endogenous processes. And you can therefore divide the exposome into internal and external exposome. And many people say it's only about exposures, but it's much more than this.
Much more than this. So it kind of leads me to the discussion I had a couple of weeks ago about epigenetics, because epigenetics is also about exposure in a way, or not?
Yeah, epigenetics is really important component of the exposome, actually. And it's often said to be the link between the exposome and the genome, because the epigenetics focuses on the environmental input on our genome. And the exposome looks at the exposures, the influences from society, from your lifestyle, from everything, and how your body reacts to it, looking at, for example, biomolecules, how your metabolism changes or everything, like the responses. And one of the responses to environmental change, for example, is also the genetic change. And if you want to link exposome and genome more, you need epigenetics.
Okay, so if you want to know more about epigenetics, you can also listen to the podcast that I had a couple of weeks ago. As I said, this was the interview with one of the guests, this time from LIH. I will also share the link in the show notes so you can check it out. And coming back to exposome, I guess, right? There should be an exposome. Coming back to exposome. So I think I kind of understood exposure a little bit more, but you were talking about historical exposome. So that's the exposure throughout history?
Well, it's a little bit more complex, I would say, because like in the exposome definition, we already said that it's looking at your lifespan. So everything that happens already from your conception until today. Researchers today are mostly focusing on the exposome, how it is today. So when they are looking at your biomolecules, at your metabolism and everything, they are looking at the present state. And they are often not considering what happened in the past, but often exposures you were facing in the past cause health outcomes that are present today. For example, with neurodegenerative diseases, we see this quite a lot. So there is an environmental factor involved in these diseases, and this is actually something that happens basically in the past. So the historical exposome concept takes into account also past exposures, but not just exposures, but also all the circumstances that were involved in your life before. And in my project, we were focusing at the last roughly 100 years. And we saw like there was, for example, here in Luxembourg, there was dust pollution happening. There was a lot of environmental contamination, and we saw a lot of society changes as well. When you are involving historical documents and historical archives into your analysis and into your research, it often gets much clearer, like what is actually the exposome. So you cannot only say the present state, I can study the exposome from the present state.
And this is a very interesting approach, because I don't think that's often the case to actually introduce the historical approach of historians and sources and archives into chemistry.
Yeah, that's right. I think most researchers don't take historical archives into account. There are some studies looking at, for example, natural archives, like, for example, botanical samples or something. There's a pine needle study by Aaron Baker, for example, which is pretty cool. Like, they really see the chemicals popping up in the different decades. But I think there should be more studies focusing as well as at historical material and also historical literature. There's so much written in the past, and also chemical measurements, for example, which have been done. Yeah, okay, they have been done with the technology which was present in the past days, but there's measurement data, and this is so important if you don't have samples present. And this was mainly the case for my study, so I did not have samples, so I had to dig into literature to get some data.
And you also had to talk to quite a few colleagues that completely were not expert in your field, right? So the whole idea of interdisciplinarity, and of course you can be an interdisciplinary researcher and study a few different fields, like, we mentioned forensic science, and you said that it was actually both biology and criminology and different fields. But when it comes to your project, so the PhD, it was also kind of crossing the Rubicon and going to C2DH, actually based also in the building where we're sitting, right? And talking to data science specialists and talking to historians and getting the help from the archives, right? How did it go? Probably in the beginning was a bit tricky. I remember I interviewed Aida, who worked with you on this project, and she was saying that, learning the language of each other is tricky, isn't it?
Yeah, it's pretty difficult. Humanities and natural sciences approaches differ quite a lot. And in some areas we speak the same language, but in most areas we speak a totally different one. And we have different approaches and methodologies to get into our research. And we had to get to a common ground somewhere, especially to write publications together and to figure out the whole topic of the exposome was for them a totally different experience and for us as well. But we learned a lot from this process, I would say.
So first of all, we should mention that the project we're talking about is called Lux Time, right? Because we did not say it, so let's say it there. And it was exactly this research of the historical exposome with your colleagues from C2DH and other researchers involved. And it was supported by Institute of Advanced Studies at the University of Luxembourg.
Yes.
Because it's, of course, pretty bold research, I would say, that kind of crossing to different disciplines. At least that's my assumption. Okay, so now that we said that, we can go further, because Lux Time was actually also based on some European projects, right? European Time Machine. Can you tell us a bit more about that project?
Yeah, it aims to be a large-scale representation of European history, culture, and society over the past millennia, using advanced digital tools like AI, big data, or machine learning. It's a lot about reconstructing and simulating Europe's past in detail. And the Lux Time project was a case study looking at just a very small region in Europe, focusing at the Minette region and the industrialization taking place in the last 100 years. So we aim to collect past data to simulate the future in the end. So this was actually the big aim to, in the end, get something out of there.
Oh, simulating the future, that's a very, very bold idea, I would say. Okay, so I have to ask you, so what was the result of the project? What can you tell us? What do we know about the future, or what did we learn about the present in this case?
Digging into the past gave us a lot of insights into not only pollution data, but also society data, like politics and everything. So from a chemistry perspective, I have to say, seeing trends in the past gave us more insight what we should change in the present to get a better future. For example, there's a lot of things happening reactionary. We're looking at chemical regulations and not precautionary. And this is one of the papers we wrote was actually mainly about this. Like, there are so many persistent compounds in our environment accumulating. And we are currently, it seems to be that we are waiting until they are getting more dangerous. But they are already dangerous and we should act right now, because otherwise, if we don't ban them now, they will be a major threat in the future.
And of course, we should here mention the important word, which is PFAS, I guess. Yeah. And if you're interested more in the discussion of PFAS and that kind of side of what LCSB does, then please listen to the interview I had with Emma Schymanski quite some time ago, but still a very, very valid and important interview. I'm just only pretty sure that the discussion of the numbers is very outdated, I would say, because of course that was quite some time ago. And unfortunately, those chemicals, they just keep increasing exponentially, I think. But talking of chemicals, I think this is the right moment for you to ask your pub quiz question today. So, Dagny, as usual, I will ask you to ask the question, and then listeners remember the answer only at the end of the podcast.
So my question would be, how many chemicals are in our environment that are currently known, looking at databases, bearing in mind that we only know the tip of the iceberg and the rest remains undiscovered so far?
Yes, so we're going back to unknown chemicals in some way. I remember talking to Emma saying like, okay, how do you discover something that is unknown? It's a bit of a detective work, right? So remember, answer to this question only at the end of the podcast. And now we come back to the discussion of the future and past and present and Lux time and everything else. But I actually wanted to ask you something about the languages that you were speaking in the project, because I think one of the biggest problems, at least from my lay perspective, is to assess the significance. So to understand, to search for it in the data that you get and then to assess it. So how do you do that? How do you know that this is significant in this discipline and that's significant in another discipline?
Well, significance varies, especially between humanities and natural sciences. In science, significance may be evaluated based on empirical evidence, experimental design, statistical analysis, and relevance to theoretical frameworks. Whereas in humanities and social science, significance may be assessed based on theoretical contributions, historical context, or interpretive insights. And it is acknowledging these differences to find a kind of interdisciplinary significance. And in order to enable, in the end, interdisciplinary work, because we have different standards and we have to come to a common ground. We wrote a lot about this in our joint manifesto paper on the historical exposome. And we had a section which was just focusing on significance, because a lot of people are not aware that there's a difference actually in the fields. And for the natural sciences, like, people are mostly focusing on the p-value, for example.
Yes.
And they are not looking at something else. I think a lot of people don't even know that there's another definition of significance.
Yes, totally. And, that's one of those words that we all understand, but then actually realize that, you meant something else, right? And I think it's also important we discuss it, because one of the big challenges, as we could say, comparing apples and pears, is when you have awards, right? When you have award for the most outstanding scientific achievement, right? And, how do you compare that? In a way, the tendency would be to look closer at natural sciences or physics or things that are kind of more, for us, tangible, because you have clearer data. And that's really sad sometimes, because we actually find it more difficult to find that significance in humanities, I believe.
Yeah, that's actually true. The research of humanities, it's often like, as you said, it's you're not having the clear data. You don't have often the objective facts, like something you can empirically analyze or anything. You often have like different viewpoints. You're approaching topics from different perspectives to actually understand them and to interpret them. And this is actually something that I became aware of, because like, there's so much more to get from data.
Yes, totally. And once again, we're kind of coming back to the discussion of C2DH. As my listeners know, I'm a big supporter of C2DH and what they do. And what I found very, very interesting was that simulation that they created about the pollution, right? So you could really see how the pollution looked like in the past.
It was the simulation we will publish now in a paper in the Journal of Digital History. It's already done through the review and everything, so we are waiting for publishing date right now. We did a simulation on dust coming from one steel factory in Laval. And yeah, it was actually pretty nice to see what you can do when you don't have actual data on chemical exposure present and what such a model can actually show. And this simulation, it was a pretty simplified model actually we used. But in the end, like, it had such a great impact. So it was published on the Minette Stories website from the C2DH. And we got such a great feedback for this because the people really saw visually what was happening in the past. And without doing these models and everything, you couldn't have done this.
Yes, totally. So do check it out. You know, the Minette Stories website is still there as well. You can check that. And yes, the publication time, we don't know probably yet, but in the latest Journal of Digital History,
yes,
you can find that. And this journal is also very interesting because last year it was nominated to the FNR award. So do check that. It's interesting also because it's a special type of journal. It's not just a printed one, is it?
Yeah, it's an online journal, and it actually has two views. So you have a narrative view and a hermeneutics view, where you actually can see the code behind the data, which is for our paper quite useful because you then actually can see how we created the model. So yeah, it's a very cool journal.
As you mentioned, code behind the data, I have to lead to another question. While working on Lux Time, you obviously had to deal a lot with data visualization, and you talked a lot to our former guest, Aida Horanie-Dibanis, about it. And of course, I had to contact her. I was like, Aida, what should I ask Dagny? So she said, ask her what she learned about data viz and what she knows now. So there you go. What have you learned, Dagny?
Data visualization was kind of new for me. Like, I knew the basic science approach to data visualization, which is very much focused on typical tools they are using, like pie charts, box plots. If you really have like your factual science data coming from experiments and everything, it's totally fine to use this. But the humanities perspective, it was opening a totally new world for me. And the different perception of data visualization is actually a super interesting field, but I think it's a study for itself. So I just got like the tip of the iceberg of this field. And I now try to use different tools than just the ones from the natural sciences, because I think the natural sciences can benefit from using tools that are used in other disciplines, as well as the humanities can benefit using other tools that are not involved in the discipline as well. This is actually something we wanted to stress in our joint research as well, that we have to look out of our box to explore different tools, to do some playful experimentation. We use the term of thinkering for this, so thinking and tinkering. So playing around with tools and trying to get something out of it that serves a broad audience, I would say. Because for science visualizations, they often just target fellow scientists. And they are pretty objective, so you cannot even approach them from multiple perspectives. But if you're looking in, I'm just saying humanities visualizations, but it's not only humanities that are using that. You're getting much more out of it. It has a different kind of dimension, I would say.
I'm really enjoying discussing it with you because you're in a way a practitioner. You're on a different side, but at the same time you've crossed, as I said, so you've seen it yourself. Because in this show, we often discuss, data literacy, the problem of people not being able to understand as we could say as scientists, I put myself in the same group, clear graph, the data is there. Why don't you understand it, right? But there is more to it. You can actually really involve the people, right?
Yeah.
And I've participated in some workshops here as well where I was a bit skeptical in the beginning because I'm this kind of very much plot pie chart person. And then I actually noticed that I still remember those visualizations because I could touch them and I could interpret them, and nobody was telling me, okay, this is the interpretation. Well, you don't get it. That's your problem.
Yeah, that's actually one of the major points. Like, science visualizations, you understand them or not, and they are right or not. And yeah, you can approach them, but you take one message out of them. Like, I'm always remembering the term like embracing complexity. So of course, a visualization should be understandable, but sometimes you have to really go and focus on one detail of the visualization and then focus on another part to actually get the whole meaning. And it might be totally different from what another person sees. It sometimes can help visualizing complex topics, like, for example, our project was as well. It's much easier to visualize our project in a complex data visualization than in a simple graph. So, yeah.
Yeah, that's the thing. This is also science communication. It's much easier to just leave the jargon and just stay where you are. But when you need to really explain with simple terms, it takes more time and it's much more demanding. And it just leads me to a visualization that I particularly liked, which are the chemical stripes that you prepared. So tell us what they were and how they worked.
So the chemical stripes are actually a visualization that is based on the idea of the climate or warming stripes by Ed Hawkins. They are not the blue, white, and red, which is the color code he chose. I chose the traffic light colors, which is green, yellow, and red. They are based on patent or literature data on chemicals, giving you an estimated value of chemical use in the past. I created an R package that can generate these chemical stripes, and you clearly can see chemical trends. So, for example, green means you have a small number of chemical patents or a small number of chemicals mentioned in respective literature. Yellow means medium value, and red is like really a warning sign. You have a lot of patents for the chemical present, or you have a lot of mentions of the chemicals in literature. We therefore wanted to show like the trends of chemicals in the past to the present to kind of show that it's really a warning sign because the trend is increasing to red. So currently we are in the red state for most of the chemicals we're looking at. Some of them have different patterns, where you clearly can see, for example, the chemical was banned in the past or something at one time point, where the patent numbers and the literature numbers decreased afterwards, which is a nice trend to see. Yeah, the chemical stripes should show you, like, it's an estimation. It's not that the patents corresponds to chemical use, but they show an estimate of how much chemicals were used in patents during that time. So.
And these are the known chemicals on top of that, right?
That's true. Like, it's just about the chemicals which are in PubChem, which have CID. Yeah. So it's just about them.
You mentioned PubChem in the interview I had with Emma. We, of course, explained it, but I think we need to remind the listeners who don't know, what is PubChem?
Yeah, it's one of the, for me, most important chemical databases out there. And it's pretty cool because Emma, like, she's my PA and she's working a lot on it. And it now has so much information available. So not only the patent data or the literature data I was talking about, but also all kinds of informations like toxicity information about transformation products, the metabolic pathways, everything you actually find in literature or that researchers contribute, because it's an open database and everyone can do a contribution. And we are always trying to get more people involved, contributing to PubChem, because it's a really good thing to understand the chemical space.
Of course, because then on the basis of that, you can actually try to identify some of the unknown chemicals. Am I right?
Yeah, on this basis, yes. If you're understanding, for example, certain pathways and how transformations are happening, you can build on this knowledge to see how chemicals might transform as well, and therefore derive other unknowns, which are not any longer unknowns then.
We moved more to the present. You mentioned before that you were saying that even in the past, in the literature, we can find, certain measurements people were taking. But of course, that was just old mechanics, old machines. So they are not, as the ones that we are using now. So I wanted to ask you, of course, about the HRMS. If I'm using the right, correct? Yes, I got it. HRMS, so high resolution mass spectrometry. Is that the leading method of analyzing chemicals right now? Or is there something newer that you're using?
We at the LCSB are mainly using HRMS for the identification of chemicals. But of course, there are other analytical methods you can use to look at the chemical space or at chemical structures. So there's IR or NMR or something like this, but this is nothing we're using. So HRMS is quite important for us because it's a higher resolution mass spectrometry. So I don't know whether I should give like a small definition of what is actually happening.
Yes, exactly. Because, I already have that knowledge, but I assume not everyone does, because not everyone has listened to all the interviews I've had. So if you can tell us a little bit, I remember with Emma, we were even discussing how big the mass spectrometer is, but just a little bit of a feeling of how it works would be brilliant.
There are actually also small devices, but most of them are pretty big and they require a vacuum, so they need a lot of space. So it's analytical technique used in chemistry to identify and or quantify chemicals based on their mass to charge ratio. So every molecule has a mass and in the end it charges well if it gets ionized. And in the HRMS instrument, you're taking your sample, it gets ionized, so it gets a charge. The ions then get accelerated, separated in the mass analyzer by their mass to charge ratio, and afterwards they get detected. And you're then getting a mass spectrum where the different compounds are separated by their mass to charge ratio. And based on this spectrum and on the abundances of the peaks, you can then derive chemical compounds. If you're thinking a chemist is just working in a lab, no, a major part of his or her research takes part actually on the computer, looking at these mass spectra and analyzing them.
That's the problem, when you have to make educational videos or like promotional videos, because in the end we could just all sit in front of computers, because most of us actually, that's how we do the science, right?
Yeah.
I prepare to my podcast, the same thing. I'm in front of a computer reading the papers. So yeah, just explain this to me. So the data that you get the raw data and then you write a program to analyze it, or how does it work? Or you have already special analytical tools available?
So there's always the possibility to use the vendor software, which is mainly doing everything you want them to do. But we in our group, we are actually working on doing everything open source. So using, for example, R packages to actually analyze our data. So the raw data, where we can select each parameter for an analysis that it fits our purpose. So with your raw data, like it's the mass spectrum with the different peaks, you're either comparing it then to databases, to spectral databases, or if you have unknown compounds, for example, you can take a look at the structure elucidation tools, which then try to come to new chemical structures.
Okay, You mentioned the buzzword. I'm just looking at my notes frenetically. And before we started recording, you already said, my PhD was about that. That was exposomics and historical exposomics. But now actually it's structure elucidation. So let's see. Are you able to explain to our listeners what that is? Because, I think I know what structure and elucidation is, but altogether, how does it work? What's this method?
So if you're having your chemical data, which is either HRMS data or NMR data, you mainly, what each researcher is doing and what I did during my PhD is looking which compounds are in the sample that we already have in databases. But with this, you're omitting so many chemicals, like a huge percentage of your measurement is gone then, because you're not looking at the unknown unknowns, we are calling them. You're looking at the known unknowns because they are already in databases. For the unknown unknowns, you have to use different tools, and this is what I'm focusing at in my postdoc. They are called CASE tools, so computer-assisted structure elucidation. They are mainly computational, often like just written packages in R, Python, or any other language. And they are trying to elucidate the structure based on the inputs you're giving it, like substructure, fragments, or anything, and the actual experimental results you have from your measurement. Then, based on this knowledge, you're running your mathematical algorithms. I won't go into detail. They are deterministic and they are stochastic methods and everything, assembly, reduction methods. And in the end, you are getting to a number of different potential structures which could exist. And you then have to look what is the probability that these chemical structures actually exist. And you then have to, in the end, it's you have to decide, or you are getting the one hit, which is then a new chemical structure. But there's a lot of mathematics in it, like a lot of graph theory, which I had to learn right now as well, like reading a lot of literature. But it's very interesting, the field. So
of course, but it means that you might get just one hit, or you might get pages and pages of possibilities, right?
Yeah, it depends on your filtering. So if you feed the program with more information and, for example, tell the program there's this fragment is involved because I see this peak, then your result list will be minimized. But otherwise, you will, for each molecular formula, you will get thousands of results. So, yeah.
All right. That's the good thing. It's not on paper anymore. For environmental reasons, it's better that it stays in the computer, but it must bring a lot of headache to you before you actually get the final result, you hope at least. And let's say you get that one hit. Yeah. And what's next?
That's the usual way we're doing it all the time. Like, you're trying actually to get the standard. You can always synthesize the compounds and then try to prove whether it's actually in your sample. So you're measuring the standard and look whether the retention time matches, whether the mass spectrum looks the same. And if it's like this, you can say, I confirm I found a new compound. And then you're writing a paper and publish it.
And then you try to actually find out where it came from, or that's not your work anymore?
This is actually something that a few of my colleagues are focusing on the different transformations. So you always have transformations happening in nature or during synthetic processes or something like this, coming from industry or so. And they're actually looking at transformation pathways. And you then always try to find out what was the parent compound of your result. But this is often it's quite easy because you have like a basic fragment structure which is involved. So for PFAS, you have a lot of time, you just have in the end like a smaller fragment, which is then analyzed because it just degraded or something. In the end, you will always find the PFAS because it's a persistent compound and it stays in the environment quite long.
Of course. I was just thinking, last thing to understand, how much of a sample do you have to actually have good results? What is the collection process? What is the size of the sample that you're dealing with?
Well, it depends on which kind of sample you're looking at. So if you're having, for example, water samples, then you have to take a look at which kind of water. So is it a wastewater sample? Is it a surface water or groundwater sample? For example, groundwater, you will expect very, very low concentrations of everything. So you have to think about up-concentrating everything. In the end, for the HRMS device, because it's so high resolution, you need a very small amount. Actually, it can measure up to ppb, sometimes even lower. But for our purposes, we use up-concentrated samples for water samples, for example, and then we are using like a few microliter. So it's really a very small amount of sample you need in the end.
Okay, it's really interesting, and it reminded me again. I just keep going somewhere with my thoughts, but I recently watched, I don't know if you know, the Takeoff show. So there's a science challenge show right now in Luxembourg where youngsters can participate and, do different science challenges. And actually just really last Sunday, although the episode is going to go live later, but still you can check. There was an episode about chemistry. And actually the last challenge that they had was they got 5 samples of water and they had to say which one is clear drinking water and which one is not. And, it was just simple tests like pH and some other compounds, but very, very interesting, of course, under stress. So I guess when you do your mass spectrometry, you're not as stressed as these poor guys were. But yes, it was very interesting as well, just testing and finding, but of course, simpler version than trying to find the unknown of the unknown, which seems to be really, really tricky, I think.
I think they were mainly looking at what we are not focusing on. Like for drinking water, for example, you're having your target analysis, which is you're having a list of your targets and you're looking whether the concentration matches or not, or whether the compound is actually involved in your sample or not. For the non-target, you have your full spectrum, you see everything that is in your sample, and this makes it often very much complicated.
And a lot to discuss still, and I hope that we will have a chance to dig deeper, maybe with your colleagues as well at LCSB about it, the transformations, as you mentioned, and everything else. And what remains right now is to solve the pub quiz question. I was really trying not to discuss everything about the chemicals and how many we have. I think we managed for the whole episode, so now we can solve. But before we solve, can you please remind our listeners what the question was about and then tell us the answer?
So the question was of how many chemicals in our environment are currently known looking at databases. And I would now mention the number for PubChem, actually. So PubChem currently has 118 million compounds. And if you remind me, it's saying that it's just the tip of the iceberg and these are the known compounds, this number is actually quite frightening, especially as new compounds are developing each day.
Yes, exactly. It's a kind of a race against time, but I have a feeling, looking also at the chemical stripes, that we're not really winning that race, are we?
Currently not. I think we know nothing about this.
And on top of it, as you said, I mean, it's the question of regulatory matters as well, and the fact that, it's not really preventive, but rather reactive, is it?
Yeah, currently we are more in the reactive phase, not the preventive.
So what we can finish with is just exactly as we finished, I think, with Emma Schymanski, was to appeal to people to come to reason and think about it a little bit, because I think the data is there. You can clearly see it. I'm going to share all the things we discussed today in the show notes, so you can see the stripes, you can see all the numbers. Of course, go to PubChem, check for yourself, open source, we said, so you can really read everything. And thank you, Dagny, so much for telling us all about your PhD and your further research in the field.
Thank you very much for having me.
And this is it for today. Don't forget to subscribe, to follow us, to check what we are writing on all the social media. And of course, we are always open to guest suggestions or just questions or anything else that comes to your mind when it comes to research done in Luxembourg. Thank you very much. This was SciLux, and my name is Hanna Siemaszko.